Yeah. Okay. Um, we we talked about sets. So we were talking about sets. We remember that if we write something like this, X belongs to A means X is a member of the set A, or X is a member of A. We talked about what is A union B. These are the X's such that they belong to A or they belong to B. We talked about their intersection. So this is all common language that we assume you know what it is and how it works. So here are a few other ones. We have a very important set, which is the empty set, the set that has no elements. There's only one of them. And we also have this operation that for us, our universe will be the real numbers. So will be the set R of real numbers. And with respect to that set, we can talk about complements. And so in general, we're going to say that a complement will be the x's that are real, but that are not in A. Okay, little example here. If we do the set to infinity as an interval in interval notation, what is this? These are the x's that are real, such that x is greater than or equal to 2. And if we wanted to do the complement of that set, well, these would be the sets that are not in here, the real numbers that are not in here. In other words, the real numbers that are less than 2. And in interval notation, this would be the set from negative infinity to negative 2, not including negative 2. Okay? So I'm just going quickly through this because I know you know what sets are and how to do unions and intersections and so on. The next concept in our preliminaries is
Professor,
function.
wouldn't it be negative infinity to 2?
Yeah, thank you. My bad. I got carried away from the negative sign of the infinity. Yes, negative infinity to 2. Yes, thank you. Next, function. So what is a function? So I will just write down here what our definition is. So given sets A and B, a function from A to B is a rule mapping each element in A to an element in B. Now let's call it F, called F of X, each element X in A to an element in B that we call F of X. And we usually write it like this. F is a function from A to B. And like we said, it takes X to F of X. A is called the domain, and the range is the set of y's in B such that y equals f of x for some x in A. All right, if I were to make a little diagram of what this function could look like, is maybe I have the set A here, the set B, and we have some mapping, some assignation f, and it takes values in here to elements over here, right? And these would be whatever elements get an arrow from from the elements in A, that's what we mean by the domain. So this orange one is the domain of F. So I'm going through this, like I said, a bit quickly because I'm counting that you know most of what I'm talking about right now. Now, you need to realize that functions can be actually quite complicated, and the book has at this point a little example of one that we're gonna see later on with more detail, but let's introduce it right now. So in the book, this is example 1.2.4, and it has a name. It's called Dirichlet function, and it's an interesting one. It's defined the following way. It's a function g such that you get 1 if x is a rational number, and you get 0 if x is not a rational number. So this ties it with what we were talking about last time about rational and irrational numbers, right? We discovered that there are some of them that are not rationals. So if we were to do the graph of this function, it would look like a little bit like this. It's kind of crooked, but so every rational number would be here. So f of 0 would be 0, f of 1 would be 0, f of 2 would be 0. If you do 1/2, it would be 0. Right, this is 1/2. If you do 1/3 and 2/3, it would be 0, etc. Right, so there's going to be a bunch of zeros here. Negative numbers as well, right? A bunch of zeros. But see here, the thing is that we also know that there are some irrational numbers, right? So somewhere over here is square root of 2, and f of square root of 2 is 1 because it's an irrational number. And we
Didn't
haven't
you?
yet.
Wouldn't it be the other way around? You said it's 1 if it's rational.
Let's change it here. As a matter of fact, let me just check. Yeah, you're right about that. Let me just check which is the right way before I mess it up even more. Yeah, so yeah, you're right about that. So then here's our way of fixing it. I'll just move my, I shouldn't have done anything here. All right, so this is not the axis, right? Just move my axis where it should be. So here is 1. So a bunch of numbers can get 1, but like something like square root of 2 would get a 0, right? So square root of 2 would be here. And like I said, I briefly mentioned it last time that it's kind of hard to come up with other irrational numbers, but we'll find out. In fact, as some of your homework problems, you can tell that if you add a rational number like square root of 2 to any, an irrational number like square root of 2 to any rational number, the answer will be irrational. So for example, square root of 2 plus 1 is irrational. We talked about it was one of the elements in your quiz, right? But you can do it with any other one, like a square root of 2 plus 3.6. That's also irrational. Or square root of 2 minus 13/7. All of these are irrational. Which makes it so that there's also a bunch of zeros here. A bunch of points all over the place that are also irrational. So it's like a difficult function to appreciate because you have a lot of elements that are zeros and a lot of elements that are ones. Okay, so I'm not meaning to give a lot of detail about this function right now. We're just introducing it for the time being. Okay, now another important definition that we should know at this point is exercise 1.2.5 or example 1.2.5 is the absolute value function. So the absolute value is defined as x if x is greater than or equal to 0, and negative x if x is less than 0. And be careful here, because even though I said negative x, this only happens when x itself is negative. So when you do the absolute value of a negative number, you put another negative sign before it, which has the effect of making it positive, right? So here, for example, the absolute value of -5, according to this definition, is minus -5. And these two minuses together actually have the effect of making it positive, right? A lot of people get confused about this because they think that this is a negative number because it has a negative sign before it, but they forget what the sign of x could be. And as a matter of fact, it's in fact positive. Okay, so some of the properties that we want to use in this class about absolute value is that it's a multiplicative function, meaning this happens for every a and b real numbers. The product of the absolute values is the same as the absolute value of the products. It's one of your homework problems to verify that. Another one is this, the so-called triangle inequality, which is that the absolute value of the sum a plus b is less than or equal than the absolute value of a plus the absolute value of b. There's a little, so again, this is also part of your homework, so I won't tell you why it is true. You can verify it. There's many ways of doing it, but I'll tell you a little bit of why it's called the triangle inequality. It's called the triangle inequality because if you apply it to the numbers a minus b, for example, and b minus c, right? If you do it with these two, it would tell you that the absolute value of that sum is less than or equal than the absolute value of a minus b plus the absolute value of b minus c. And if you simplify this, of course, I put minus b plus b. This is a minus c. And then here's the important thing about something that you would be, it would be to your advantage to remember. The absolute value of a minus c, a different way of thinking about it, a geometric way of thinking about it, and by that I mean, you know, with a picture, is to think of this as the distance from A to C, right? And it is convenient because you don't need to know which of the two numbers is bigger, right? So if I ask you what is the distance from the number 5 to the number 8, well, you usually what you do is you take the bigger one and you subtract the smaller one, right? So you do 8 minus 5 and you get 3. But if you follow the formula that I just gave you, then it doesn't matter if you do it the other way around because you have the absolute value. If you do it the other way around, it would be 5 minus 8, that's negative 3. But the absolute value of negative 3 is 3, and that's convenient, right? Because then you don't need to identify which of the two is the largest. You can write it in general as the distance from A to C. And now this is why it's called the triangle inequality, because what this inequality is telling you is that the distance from A to C is smaller than the distance from A to B plus the distance from B to C, right? You can call this the distance from A to B, and this one the distance from B to C. And if you were to do that, not in the real line, but say in the plane with points, right? I could put A here and B and C and draw a triangle. Then what this is telling us is that this distance from A to C is smaller than if you go from A to B and then from B to C. Sort of like saying that in the sum of the two sides of a triangle are always greater than the other. Or in a different way, that the shortest distance between 2 points is a straight line. So this is a shorter distance than going here and then there. Okay, and that's the reason it's called the triangle inequality. Okay, what else? Another thing that we will use and assume that you know about is the concept of proving things by induction. So I'll just briefly review that, what I mean by that. So you should all have taken 320. So you should know what I'm talking about here. And this is the principle of induction. If you have a set of natural numbers and it has the following two properties. One, S contains 1. And 2, whenever n belongs to S, n plus 1 belongs to S. If you have a set that has those two properties, then that set is actually all the natural numbers, right? And this is very useful when you want to prove that a property holds for the set of natural numbers. What you do is you do precisely this. You show that the first number, the number 1, is in there. And then you show that whenever a number is there, then the next number is there as well. Let me show at least a little example of this. This is example 1.2.7 in our book. And we're gonna define a sequence of real numbers. The first element in the sequence is going to be 1. And then the nth plus 1 element will be defined as multiply by 1/2 the nth element and then add 1. And what we need to do is to show that xm is less than or equal xm plus 1 for all m natural numbers. Okay. And then how do we do this by induction? So here's the proof. So we call S the set of m's that make this work. So these are the natural numbers that have the property we desire. That's our set S. And then we verify what I told you. So we check that, is it true that the number 1 belongs in that set, right? So that's our first question. Is 1 an element in S? We ask ourselves. And how do we check that? Well, we would need to check that x1 is smaller than x2. So let's figure what those are. So we know that x1 is 1. And we know that x2 is, according to our definition, is 1/2 x1 plus 1. But this guy is 1, so this is 1/2 times 1 plus 1. So that's 3/2. And that's great because indeed this happens, right? 1 is less than 3/2. So the fact that this inequality is true tells us that 1 belongs to S. We call this the basis of induction, by the way. And the next thing, we call it the inductive step, which is what I'm going to do now, right? How do we do the inductive step? Well, we assume, in this case, I'm using M instead of N, but that really doesn't matter. We assume that M belongs to S, and we see if we could use that information to show that that same property holds for the next number, for M plus 1. So we assume M belongs to S. We call this the induction hypothesis. And then we try to prove that the next one works as well. And how do we do that? Well, the fact that M belongs to S means that xm is less than xm plus 1. So this means that xm is less than or equal than xm plus 1. But what is xm plus 1, right? That would be good to remember. Xm plus 1 is 1/2 of xm plus 1. Okay, and then what do we want to prove? So this is what we know. That's the induction hypothesis. And then what we want to prove is, let me write it here in red. We want to prove that xm plus 1 is less than or equal xm plus 2. But we haven't done it, so that's why I'm putting it in red. You need to be careful where you write down what you want and you haven't done it, because someone that's reading your write-up may think that you're assuming what you want to prove, and that's a big mistake. Okay, so how do we do it? Well, let's try to figure out what is xm plus 2. By definition, xm plus 2 is 1/2 of xm plus 1 plus 1, right? And then what I need to argue is, why is it that this number is bigger than xm plus 1? Okay? And it would be nice if at some point I use this, right? I better use this, otherwise that means I'm not using my hypothesis. And sometimes you can do it, but then it's not really a proof by induction. It means you could have proven your inequality without using the previous one. Okay, so how am I going to do it? Well, I'm going to realize that this number xm plus 1 is bigger than xm. And so if I multiply this inequality by 1/2, it keeps going. And if I add 1, it still verifies as well. So what I meant to say here is that, running out of space, what I mean to say here is that this is greater than or equal xm 1/2 of xm plus 1, correct? Because this guy is bigger than this. I'm using right here my hypothesis. So this is used right here. And then the kicker is the final part, is that this expression over here, as you can see from here, is exactly the same as xm plus 1. So now if you read this from the first to the last, what it says is that xm plus 2 is greater than or equal xm plus 1. Hence, m plus 1 belongs to S. And then by induction, because I know 1 belongs to S, and every time a number belongs to S, the next one belongs there as well. By induction, I can conclude that S is the entire set of natural numbers, right? If you,
Professor?
yes.
Can you explain how you got xm plus 2 equals 1/2 xm plus 1 plus 1?
Why xm plus 2, this one?
Yeah.
It's the definition, right? If I go up to the way the sequence was defined, look how the sequence is defined. To get the nth plus 1 term, you take the previous term, you multiply it by 1/2, and you add 1. That's the way this sequence is defined, right? Maybe I can do a few. So we start with 1. After that, you get 3/2. Then, so this is x1, this is x2. What would be x3? It would be multiply 3/2 times 1, so you get 3/4, and then add 1, so that's 7/4. And then the one after that would be multiply this guy by 1/2, it would be 7/8, and then add 1, so that would be 15/8, and so on. Is that clear?
Yeah.
Good. I'll put it here. And the only thing that I added here is that all of these, where we started assuming m belongs to S, and where we finished by saying m plus 1 belongs to S, all of this is called the inductive step, right? So this is the basis of induction, checking that 1 belongs to S, and all of this is the inductive step. And which shows that we are done right there. Okay, so there's a few other things in chapter 1.2 that I did not go over. So it talks a little bit about logics and proofs, but you can at your leisure read and make sure you're familiar with all of that, right? In essence, those are the prerequisites for this class. So knowing that you have some idea of how proofs work, right? How to do a proof, a direct proof, a proof by contradiction, and in this case, a proof by induction, which is the one that I at least gave you a little bit of an example. Okay, so now we're gonna move on to the next section. So the next section is 1.3, which is where we finally going to talk about this question of what makes the real numbers, right? What makes it different from other sets? Just get more paper, okay? And here's where we are. So this is 1.3. It's called the section is called the Axiom of Completeness. And at this point, it's probably a good moment in our class to tell you that we won't have a quiz today like we did last time, but we will have one at the beginning. I'm telling you in advance, at the beginning of next class, and it will be about 1.3. Okay. All right. So what is it that we know about the real numbers at this so far? So here's where we are so far. We know that the real numbers are an extension of the rational numbers, and we know that there are no holes, with no holes or gaps, right? The reason we know that is because we like to think of the real numbers as the real line, right? The entire real line. And we already saw that the rational numbers have holes, right? Because in between two rationals, it's not true that all of them in between are rational, right? Maybe we'll revisit that with more detail. I mean, I know you know already that. I know we haven't proved it precisely, but the rational numbers have holes, and we don't want that. We want to, that's exactly our point right now. How do we say this part over here precisely, having no holes or gaps? This is the important thing. How can we say no holes or gaps? Fix this. No holes or gaps. Okay, so here is a possibility of an initial definition. So here's an initial definition. Something that we can try for an initial definition. Here we go. So maybe we want the following. We want the real numbers to contain the rationals. Yes, that's a good point. We also would like for the operations of addition and multiplication to extend, should extend to R, right? I mean, we should be able to add real numbers and multiply real numbers. I'm sure you want that. So in other words, every real number should have an additive inverse, and every non-zero real number should have a multiplicative inverse, okay? So, i.e., every real number should have an additive inverse, and every non-zero real number should have a multiplicative inverse. And then more properties that we would like, right? We would like for the real numbers to also be a field. Remember, we talked about a field. So it means that the operations of addition and multiplication are commutative, associative. We already know that we have neutral elements or identity elements, and we have inverses. And plus there's the distributive property between them. So let me write it here. In fact, we would like for the real numbers with addition and multiplication to be a field. And I went over that already. I don't want to write down what are the properties of the field, but I said them already. Okay, and we also wanted it to be an order field like the rational numbers, right? So we also want a total order on R, like an extension of the order that we have in the rational numbers. So we want to say that every two real numbers are either the same or one is greater than the other. That would be fantastic, right? So maybe you're thinking, okay, that's fantastic, Professor. So this is our want list. So maybe all we need to do is say, well, the real numbers is a set that has these properties, right? So let me write it here more precisely. We want the real numbers to be an ordered field that contains the rational numbers as a subfield, right? So what I mean by this is that the rational numbers are inside the real numbers, and the operations on the rational numbers extend to the real numbers. And maybe, like I was telling you, maybe this is enough. And sadly, that's not the case. Okay, so let me write it here. Sadly, this is not enough. And I'll tell you, for those of you that have taken 360, probably you already have an idea of why this is not enough. Well, it turns out that there are fields like that have this property, and that they are not the real numbers. See, for example, there's this field, Q root 2. If you've never seen it before, don't worry too much about this remark. You'll learn a little something, but I'll tell you what it is. These are very specific sets of numbers. They're numbers like these. They look like this: a plus b root 2, where a and b are rationals, right? So for example, in particular, you have all the rationals are in here because you can make b 0. If you make b 0, then they belong in here. You can also make a 0. So you also have any rational number times the square root of 2. So for example, 2 times the square root of 2 is there. 10 times the square root of 2 is there. Negative 3/16 of the square root of 2 is there as well. But also the combinations you can create with these two. So 1 plus the square root of 2 belongs in here as well. And I'm not going to do it right now because this is not 360, but you can check that when you multiply two numbers like this, you get another number that looks like this. And when you add two numbers like this, you get another number that looks like this. So it is indeed a field. And you can find the inverse of a multiplicative inverse of every one of these numbers, and it's going to look like one of these, etc. Right? So take my word for now, if you've never done it before. It's not hard, actually. It's actually quite easy. That this guy is a field that contains Q. And it's obviously ordered as well. You can compare any two numbers. And the problem with this guy is that it has holes, all right? A little bit just like the rational numbers, this field has lots of holes. So Q root 2 still has holes. So it doesn't work to simply ask for this nice list of properties we wanted. So there is something else that makes the real numbers the real numbers. Good. So now I'm going to tell you a little bit how we're going to proceed, because we're not going to do it in an axiomatic way. Let me actually put myself on the screen, and we'll talk about, and so you can see me when I tell you this. So if you wanted to do this on an axiomatic way, this is what you would do. You would construct the real numbers, right? So we want something that has this property that has no holes. So what we should do, if we wanted to do it, build from nothing and grow, would be to construct the real numbers. And unfortunately, that's actually quite hard, right? We don't even cover it in an undergraduate degree, I believe. So, I mean, if you're curious, our book does it at the very end. it has a chapter where you can actually construct the real numbers. So we won't do it like that. And there's several ways of doing. There's a thing called doing it by Dedekind cuts or with Cauchy sequences. Several ways. There is more than one way of doing it. And it's complicated. And you wouldn't learn too much from it, right? It would be like wanting to learn about the way a building works by, you know, starting to lay brick or, you know, construct, putting the starting from the bottom floor and at the basement. You wouldn't see how the entire thing works. So that's not what we're gonna do. The way we're gonna go around it is we're gonna, I'm gonna tell you what is the property that makes the real numbers, and we're gonna call that an axiom, right? And here I should tell you what we mean when we say an axiom. An axiom is a property that we're not gonna prove. An axiom is a property that we're gonna assume is true, without question, right? We're gonna assume that this property holds. And not surprisingly, because that's the name of this section, this axiom is called the axiom of completeness, all right? So later on in your lives, when you're more mature mathematics students, maybe you will revisit this and construct the real numbers and then show that the real numbers you constructed have satisfied the axiom of completeness. And then once you do that, then all the properties we're going to work on from now on, based on this axiom, you will know they are true because the set you constructed will have to satisfy the axiom on which everything is based. So that's what I'm going to do now. And without further ado, I'm going to now tell you what is this axiom, right? What really makes the real numbers, okay? Well, let's go back to the page. Okay, so the axiom of completeness. The axiom of completeness. All right, so here it is. Here, this is what it says. It says every non-empty set of real numbers that is bounded above no comma has a least upper bound. Okay, so there it is. That is the axiom of completeness, and we're going to explain it, right? We're going to explain all the words that are here, right? So what is it that we need to explain? We can tell right away. Well, non-empty, I think we understand what it means, right? It means it's not the empty set. And then we need to explain what is the meaning of bounded above and what is the meaning of least upper bound. Okay, so we'll go through those. Don't worry. So let's start with definition 1.3.1. And this is what it means to be bounded above. Okay, so as set A, subset of the real numbers, is bounded above if there exists a number B, that's the bound, such that A is less than or equal to B for all A in A. All right, let's understand. So we say that a set is bounded above if there is some number which is bigger than all the elements in A, right? So in other words, if you draw A on the real line, there is some number B, and you can tell that the entire set is before that number B. So let me make a little picture here of what the situation is. So here's the real line, and maybe your set is like this, all of these, and then maybe a sequence here, maybe some isolated points, maybe another segment, but then that's it. So how do I know this set is upper bounded? Well, because I can find a number over here, B, and this number B is to the right or of everything in A. Okay, this is A. Good. So that's the first definition. And I'll just continue a little bit saying a few more things about this. The number B is called an upper bound, not surprisingly, for A. And similarly, we can also, we did it bounded above, but we can also define bounded below, right? You may be wondering, hey, Professor, why are we giving preference to the right side? Can't we do this the same on the left side? And yes, you would be right about that. And it's just a matter of, well, the fact that right side is positive and we all prefer the positive over the negative. No real reason there. So similarly, the set A is bounded below. That's the term we're learning. Bounded below if there is a lower bound, L, a real number, such that L is less than or equal A for all A in capital A. And you'll notice that this time I'm already calling L a lower bound, right? So I didn't say that number L is called a lower bound. I sort of put it in that definition, right? Okay, so that takes care of let's go to the top a little bit. That takes care of this part, right? What is the meaning of bounded above? Now let's talk about this part. What is the meaning of the least upper bound? And then, of course, we want to understand all of these by looking at some examples. So here's our next definition, 1.3.2 in the book. And it says the following. It says a real number, S, is the least upper bound for a set A, subset of the real numbers, if it meets the following criteria. The following criteria. There's only two things. One, S itself is an upper bound of A, right? Makes sense. We're calling it the least upper bound, then we expect the number to at least be an upper bound. So S is an upper bound, that's the first one. And two, if B is an upper bound, then S is smaller than B. Makes sense, right? So in other words, this is a different way of saying it. This second property is telling us that S is the smallest of all the upper bounds, right? S is the minimum of all the upper bounds. The smallest of all of them. In this sense, if you find any other upper bound, then S has to be smaller than that. Okay, and let's draw a picture here. Well, actually, let's go back to the picture that I had drawn already, right? Now, could this guy be the least upper bound?
No.
Why not?
There's smaller numbers before that.
There are smaller numbers that are still upper bounds, right?
Yeah.
So this B is not the least upper bound because maybe I can now look at this guy over here, right? And which is even smaller than this one. Now this one is still not the upper bound, right? Because I could go here. So where is the least upper bound? Well, hard for you to answer because you cannot point to my drawing, right? But the least upper bound in this drawing would be right here, correct? Is the end of this blue segment. That this would be the least upper bound. Okay, so a few remarks and more explanations. First remark is that this least upper bound is a mouthful, right? So as we mathematicians usually do, we came up with a term that is just one word. So instead of saying least upper bound all the time, we call it the supremum, okay? That's just a short way of saying least upper bound. So note one, we use the word supremum as a synonym of least upper bound. And that's convenient because we also have a term for it. So if you want to know the supremum of a set, so the supremum of a set A is, we call it sup A. So it's like the abbreviation of the abbreviation, right? Even more compact. So another way of saying the axiom of completeness, let's go back. This axiom of completeness is to say that every non-empty set of real numbers that is bounded above has a supremum, right? So instead of saying all of these, we could say supremum. Good. So that's note number one. Note number two is that, like I was telling you, I mean, we gave a preference to the right side just because, but we could have done this on the left side, right? And you can do it on the left side. So we already know that we can talk about lower bounds, and then we could talk about the greatest lower bound, right? So let's go back to our picture. So this set also has lower bounds. The lower bounds are right here on the left. And because it's a set that is bounded below, we could argue, and we will do it later on, that there is the greatest of all the lower bounds. And the greatest of all the lower bounds is called the infimum. That's the corresponding symmetric term. I'm going to write it here. So similarly, we define the infimum as the greatest lower bound of a set A. The infimum of A as the greatest lower bound of a set A. And there's an exercise where you're asked to verify these and to check that you don't need to add it to the axiom, right? You may be wondering, hey, professor, maybe we should have in our axiom that every non-empty set bounded above has a supremum, and also that every non-empty set bounded below has an infimum. And it turns out that we don't need that. It's enough to have one of them. If you have one, you can prove the other one, right? So mathematicians, we're also very economical. We don't want to add things that are unnecessary. So we look for the smallest thing that is enough. And here, like I said, we just gave preference to the right side. So the axiom will be that non-empty sets bounded above have a supremum, but We could have done it the other way around. We could have said that the axiom will be every non-empty set bounded below has an infimum, and it would work also. So either way would work nicely. Okay, so good. So then remember that this is what the axiom is telling us. The axiom is telling us that every non-empty set, which is bounded, right, has to have a supremum. We're not going to question that. We're going to use that property, okay? And what we are going to do is I'm going to show you. I was hoping today, but maybe we don't have time. Maybe next time. I'm going to show you that that property actually is inherent to the real numbers. So, for example, the rational numbers fail that property. The rational numbers don't have that property. So this is a way of saying that the other set that I told you before, Q with root 2, also does not have this property. Okay, that would be harder for me to tell you at this point, but this really is a property that makes the real numbers the real numbers. This is really something that distinguishes the real numbers from the rationals. And it is also a way to saying that it has no holes and no gaps. Okay, let's do an example. This is example 1.3.3. And we are going to consider this set, which you guys know quite well, the set of 1 over n, where n is a natural number. So let's start listing a few of the elements here. So this is 1, 1/2, 1/3, 1/4, etc. Right? I cannot do all of them. It looks like this. And what we want to do is we want to find out what is the supremum of this set, what is the infimum of this set. So let's start with the supremum. Well, first of all, does it have a supremum, right? Because we need to verify, to use the axiom, we need to check that is non-empty and bounded above. Okay, so let's start with that. Is it non-empty?
Yes.
Obviously, right? And how do you convince me? How do you convince someone that a set is non-empty?
It has elements in it.
Yeah, you show an element, right? Is A non-empty? Yes. And because, well, I'm going to pick 1. 1 belongs to A. But if you pick 1/2 or 1/5, it will work as well. Is it bounded above? Right? Is there an upper bound to this set? Is there a number that is bigger to all the numbers?
1. Yes.
Which one would it be?
1.
1 works, right? But
Yeah.
you could have picked another one, like I'm going to pick 10. So yes, because I'm going to say because 1 over n is smaller than or equal 10 for any n natural number, right? Of course, because this number is 1 or 1/2 or 1/3, they're all, well, like you said, they're all smaller than 1, but I didn't pick 1. I pick another bound, right? But you're already on the right track to answer the next question. So, okay, because the answer to these two questions is yes, we know by the axiom that the supremum exists. So then we know supremum of A exists. There has to be the least of the upper bounds. What is it?
1.
Yes. So the supremum of A is 1.
And wouldn't it also be a maximum? Because it's contained in the set?
Good. I haven't defined the maximum, but that's where I'm going with this. But yes.
So when you say, like, is it bounded above and you do 1 over n less than or greater than 10, like 10 doesn't have to be part of the set?
No. No.
You say as long as it's less than any number?
Correct. Yeah.
Oh.
Yeah. The number 10 does not need to be on the set. It's just an arbitrary real number. So here the supremum is 1, and someone already said that it's in fact the maximum. So hold on to that thought, because I'll properly define what a maximum is. But you were right about that. So so here the supremum is 1. Why is it? Because 1 is definitely an upper bound. And if we have another upper bound, right? And if B is an upper bound of A, then in particular, see, if this guy is an upper bound, then in particular, B has to be bigger than all of these guys, right? In particular, B has to be bigger than the first number that I wrote here, because this is one of them. Then B is greater than 1, right? Because 1 belongs to A. Yes? And I just show you then 1 has to be the least upper bound, because any other upper bound is bigger than 1. Mm-hmm. In other words, the supremum is actually 1. Mm-hmm. Okay. Now, what about the infimum? Is there an infimum first? Is this set A bounded below?
You'll never get 0.
Okay. Let's go step by step first. Is it bounded below?
Yes. Yes.
Yes. So what would be a lower bound?
-5.
Good, right? So it is bounded below and it is non-empty. So it should have an infimum. Mm-hmm. So let's write it here. What is infimum of A? Note that, let's write it here, note that A is non-empty and bounded below, say by -5, like you said. Mm-hmm. So what would be the infimum?
0.
It is 0, right? And but notice how the difference here. This time around, 0 is not a member of the set, right? For the supremum was 1, and 1 belonged to the set. Yes. So this is very important. That's what's so, in my opinion, why this example is important that we go over it. See, this example shows you that the supremum may or may not be a member of the set. The same thing with the infimum. The infimum may be a member of the set or maybe may not be a member of the set. Okay, it depends. Mm-hmm. But it exists. That's the important thing. So the infimum is 0. The infimum is 0. Now, I cannot actually prove it thoroughly just yet. I mean, I can, but we're going to go over some propositions that we're going to help you argue these in a better way. Now, I can argue that it is a lower bound, right? The infimum is 0. Indeed, 0 is less than or equal 1/n for all n natural number. So that means 0 is a lower bound. But what I cannot yet do, or I don't want to at this point, is to show you that it is the greatest of the lower bounds, okay? I could, but like I said, we're gonna wait a little bit more to argue. So let's hold on to that idea that we're not totally finished with this exercise. We want to argue why we haven't answered this question thoroughly, like we did for the supremum. See, check the one for the supremum. For the supremum, we checked the two things. We checked that 1 is an upper bound right here. And we also checked that it's the least of the upper bounds because we consider any other upper bound and we show that B is greater than or equal 1. Mm-hmm. Okay. And this also illustrates the next definitions, which is the definition of a maximum and a minimum. So let's write it here. This is definition 1.3.4 in our book, and it says the following: a real number A0, a real number A0 is a maximum of the set A, a subset of real numbers, if A0 belongs to A and A0 is greater than or equal A for all A in A. Similarly, a real number B0 is a minimum of A if B0 belongs to A and B0 is less than or equal A for all A in A. All right, so based on this definition, the supremum that we did on the previous one was in fact the maximum, right? Because it belonged to the set. And this illustrates that that can happen or that cannot happen, because what is the minimum of this set?
Doesn't have one.
Yeah, right. So a set, there is no axiom that tells you every non-empty bounded set has a minimum. That axiom does not exist, right? It's not true. Here's an example that shows it's not true, right? So the axiom tells you that there is an infimum or that there is a supremum, but it doesn't tell you that there's a minimum or a maximum. Sometimes there isn't. Here there is no minimum, right? So there is no guarantee that you get maximums or minimums. What it is true, though, is that if a set has a maximum or a minimum, then that's automatically the supremum or the infimum, okay? But you need to then show it is the maximum. So what it is true is, so note, if A0 is a maximum, now I'm saying a maximum, but it should be the maximum, right? But that's something you need to argue, that there is only one of A, then A0 is the supremum of A. If a number is the maximum, then it's automatically the supremum. Why? Let's explain it. Well, the number it's obviously an upper bound, right? Because it's greater than or equal by definition that every element in A. So I'm gonna prove this. That's what I'm doing. Because A0 is a maximum of A, then A0 is greater than or equal A for all A in A. Correct? I just wrote the definition. And this means that A0 is an upper bound. So A0 is an upper bound of A. Okay, good. Now, how do I show that it is the least of the upper bounds? Well, let's suppose we have another upper bound. Suppose B is an upper bound of A. That is, B is greater than or equal A for all A in A. Good? Well, but here's the thing now, right? If B is greater than or equal than any element in A, in particular, because A0 belongs to the set, right? Here's the definition. Let me scroll a little bit. See, this is part of the definition, right? A0 is in A. So because A0 is in A, we know that B is greater than or equal to A0. Because A0 belongs to A, then B is greater than or equal A0. And that shows that then A0 is smaller than this other upper bound, which means A0 is the least of the upper bounds. And that means that A0 is the supremum. So if you have a maximum, it's automatically the supremum. If you have a minimum, it's automatically the infimum, because of this little note that I just proved to you. Okay? Questions so far? I'll do another example before we talk about why this property doesn't hold for the rational numbers. So here's another example with some very familiar sets. So this is example 1.3.5 in our book. All right, so what if we now consider this set, the open interval 0 to 2. So these are the real numbers that are strictly between 0 and 2. Okay, is this set upper bounded?
Yes.
A bunch of numbers, right? 3, 4, 5, etc. So it is non-empty because there's a lot of elements between 0 and 2. For example, 1 belongs in there. So let's say 1 belongs to A, and 3 is an upper bound. So it must have a supremum. What is the supremum?
Two.
2.
Yeah, it is 2, right? Now, it's for these problems, it's easy to figure it out. It's harder to prove it, right? So how do we prove that 2 is the supremum? You need to check that 2 is an upper bound. That's easy, almost by definition here, right? This part over here. And you need to check that it is the least of the upper bounds, right? And that's a part that we are not going to do just yet. So supremum of A is 2. So we can check 2 is an upper bound by definition. But we won't check that it is the least of the upper bounds just yet. Like I was telling you, we're gonna write down a lemma or a little proposition. It's called a lemma in a book. And using that lemma is gonna be quite easy to check this. So we're gonna come back to that. So for now, it's an incomplete exercise. But let's consider now this other one, very similar set. Now it's the interval where it's open on the left and closed on the right. And the same thing happens, right? 1 belongs to A and 3 is an upper bound. So 1 belongs to B, 3 is an upper bound. So this set must have a supremum. What is the supremum?
2.
Yeah, it's again 2. But in this case, we can't check it. Why? Because this happens to be not only the supremum, but the maximum, right? In this case, here, in fact, the maximum of the set B is 2. And how do I check that it is indeed the maximum? Well, I need to check 2 things. I need to check that it belongs to the set. Does 2 belong to B? You bet, right? Because it satisfies this inequality. And is it an upper bound? You bet, because it's right here. 2 is greater than or equal x for any x in B. Indeed, 2 belongs to B, and 2 is greater than or equal x for every x in B. So the maximum of B is 2. And we already said that if something is the maximum, then it is automatically the supremum. And these 2 examples together, again, bring, I hope, solidify this fact that the supremum may or may not belong to the set. So the supremum is the number 2 for both examples, right? The supremum was 2 here and is also 2 here. But over here, the supremum is not in the set A, and here the supremum is in the set A. Okay, so don't make that mistake. The supremum may be in the set or may not be in the set. You don't know. When it is in the set, then it's called a maximum. But some sets have no maximums, right? It's a different way of saying what I just said. All right, so last thing we're gonna do today, and this is example 1.3.6, is how come this property does not hold for the rational numbers? How come U does not have the axiom of completeness, or does not satisfy the axiom of completeness? Right? How can we check that? And it's easy if I show you an example where it fails. So I'm going to show you an example where we have a set that is non-empty and is upper bounded, but does not have a least upper bound. So here is a set S, which is non-empty, upper bounded, but it has no least upper bound in Q, of course, in Q. So imagine what we're trying to say here is imagine our universe is only the rational numbers. So for the rational numbers to have the axiom of completeness, we should have that every non-empty upper bounded set has a least upper bound that's also a rational number, right? In our universe, it is not, of course, it's going to have a least upper bound in the real numbers because we know the axiom of completeness works in the real numbers. So here's the set. The set is, these are going to be the rational numbers such that R squared is less than 2. Okay. Does this set have an, is it non-empty?
Yep.
Yeah. S is non-empty. Show me an element.
1.
1. 1 belongs to S. Awesome, because 1 squared is less than 2, right? Does it have an upper bound? Is it upper bounded?
Is the upper bound in the rationals or
Yes.
just?
Yes.
2.
2 is an upper bound, right? Yes. 2 is an upper bound. How do we check that? Well, suppose you have an element in S. If R belongs to S, then R squared is less than 2, correct? By definition. But 2 is less than 4, right? So then that means that the number R is in absolute value less than 2. So that means that both the number and its negative are less than 2. So this in particular means that R itself is less than 2. So it is bounded by 2. Now, what would happen if we want to find out the least upper bound? And we're about to be done here, by the way. I know I'm already at 1:45, but we're almost done here. So what would be if we wanted a least upper bound? So this is the upper bound 2. What would be a better one? An even smaller one?
1.5.
Square root 2.
Yeah, 1.5 exactly, right? 1.5 is even smaller. So that will work, right? And then if you want to keep going, you would go, okay, what about 1.42? And you can check that that one works as well. See, all I need to for it to work is that when I square this number, I get something bigger than 2, right? I can, that was my trick here. The way I made this work is, this is 2 square, right? So if this number square is still bigger than 2, then it works. And then this is even smaller. And then, well, I can keep going. I can go 4, 1, 5. And then after that, I can go 1.4, 1, 4, 2. And then after that, I can go 4, 1, 4, 1, 4. I'm doing this right. 4, 1, 4, 2, 3, 5. Yeah. 4, 1, 4. And then 1.414136. What am I doing here? Where am I getting these numbers? So if we were doing it over the real numbers, what would be the upper bound? The least upper bound.
Be the square root of 2.
Yes, it would be the square root of 2, right? And that's why this one does not work here, because we already know that the square root of 2 is not a rational number, right? However, I can get as close as I want, right? So we know that square root of 2 is about, so if you get the decimal digits, is like 1.41413570, etc. There's more here, and it keeps going on and on and on. So if I keep using more and more digits, I can get upper bounds that are smaller and smaller every time, but I will never ever reach the least upper bound, which is square root of 2. Okay, is that clear? So there is no least upper bound in Q. So that's why this property of having a least upper bound doesn't work for the rational numbers, right? I mean, of course, there is a least upper bound, namely the square root of 2, if you extend it to the real numbers, because we know that axiom works for the real numbers. Okay? So in other words, the rational numbers have a whole, right? This is a different way of explaining this exercise. Why it contradicts the property is we have a whole. There is a whole at square root of 2. We know square root of 2 is not rational. So if we pick a set that has that as that number would be the supremum, then that number, because it's not a rational number, will not be able to satisfy this property of every non-empty bounded set having a supremum in the set. Okay, so I'm gonna stop right here. Like I said, we'll finish up this section 1.3, and we'll have a little quiz at the beginning of the session next week. All right.
On 1.3.
On 1.3, yes. So enjoy your week, guys.
Thank you, Professor.